We will be talking about game theories here. I'm Daria. I'm an SRE. This means that I walk around and explain people all the ways their systems failed. And today we will talk about reliability failures and how those are not an engineering blame. And why? Because they are not caused by bad decisions. They are caused by the rational decisions that are locally optimized and made in the scope of the global game. And you as an SRE actually can redesign this game, those game mechanisms. So we will learn a few games today, and we will see how we can redesign them to bring all your team and all your organization to better outcome. So since I'm a visual storyteller, you will see a lot of AI-generated pictures that sometimes don't make sense. There are bunnies and piglets and all kind of things, but it just helps me to tell the story. And also, disclaimer, any opinions in this talk are my own and not of my employer, so just take it. And I'm not a game theory expert. I learned it for this talk. Well, it's actually started funny. Same way as one of my previous talks on Dungeons and Dragons that started with watching movie. This one also started with watching movie about game theory professor. And I was thinking, I should submit a talk to SREcon, but what about? But look, this game theory thing, which is very mysterious and helped someone to solve very complex problem. Why don't I just learn it and apply it to SRE? And as a result, you have this talk. Long, long time ago, I would like to say centuries, but it's 8 years ago. To be precise, I attended my very first SREcon. It was in Germany, Düsseldorf. This is when I met all the lovely SRE people who became my friends now. And in the hallways, we had a ton of different conversations. We spoke about how to start with observability and how to do noise reduction, SLOs, how to deal with legacy systems, and how to get other teams to commit to reliability work. That's 2018. Many things happened since then. We have this fantastic new picture of Saturn released by NASA. I think it's amazing. There's new Hubble telescope and the Webb telescope. Other things happened. We survived toilet paper outages. And everyone can use AI now. Probably everyone have AI in their pocket at this moment. So isn't it amazing? And also everybody was putting their pets in the decks, that whoever had pets. So I thought I will add my pets because this is something that changed since my very first SREcon. Now I have a cat and now I have a dog. And one of the top questions to speakers who put pets in their deck was, what's your pet name? It's extremely relevant for the engineering discipline to name your pets correctly. That's why I'm adding names here on the screen. And the Azure, it's because she is blue, just for the context. Okay, so, and also other things happened since my very first SREcon. For example, I read a book, and then I read another book. Unfortunately, I finished with more questions than I had before I read those books. But now I heard there is another book coming, and I'm really looking forward because really this book will answer those questions. So I finally will get it right. So I'm looking forward, folks who are writing this book, really looking forward to that. And then this week, we had so many fantastic discussions, and we took notes. Well, when I wasn't preparing for this talk, we were also taking notes. And from observability discussion track, there were some learnings that I would like to share with you. So some of the popular topics were how to start with observability, how to do noise reduction and SLI SLO, how do we deal with legacy systems, how to get other teams to commit to reliability work, and there was a new one. But we just reviewed this 8 slides ago. I know I counted that was 8 slides ago. So 8 years, and we still have the same challenges. What's going on? Why do we still have those problems? We have 2 books already, so we... because it's not about who failed. It's about what system made the outcome likely logical. And we all have good intent. We are making rational decisions, and we're still getting unexpected outcomes. So what's going on? Well, people don't create accidents. Systems do. This is the paraphrased safety literature. And SRE is not a single player problem. We are here in this together. We take decisions based on the information we are provided, and somehow, globally, it may not work or it may work. And good decisions sometimes combine badly. This is AI generated, so if you find any extra legs, not my fault. So why did I choose game theory? So I already mentioned that I got inspired by watching a movie, and I just thought game theory seems to be a very interesting topic to learn. And I'm a mathematician, but game theory wasn't part of my curriculum, and I just thought, well, why not? So I started with buying 2 books again, because I always start with buying 2 books for redundancy. And then I watched a few online videos from different universities to be able to give you some knowledge here. So, game theory studies situations where outcomes depend on multiple reasonable actors making interdependent choices. That's the definition. For example, the traffic and the roads, markets, or SRE, because we all make a lot of decisions. And there's a concept in game theory defined as Nash equilibrium, which is the state where everyone is doing the best thing for themselves, and the overall system return the result, and nobody can change the outcome for better if they act alone. But remember, Nash equilibrium doesn't mean good. It just means that the system is stable, and if one person cannot optimize the outcome of the whole system just by acting alone. So it just means it's stable. And maybe your system may have settled in the bad equilibrium, because you may still have problems. And because SRE work is highly technical, most failures aren't actually technical, they are coordination failures. And game theory studies this very deeply. I decided that that doggy that everyone puts in the picture with "that's fine" should be AI'd. So this doggy says 0 days since the last outage. And game theory explains why smart, well-intentioned teams can repeatedly produce bad outcomes, and how changing the rules changes the outcome. And we will also talk about culture. Culture is actually a result of some game models as well, and something really exciting to learn. So SRE job in this talk, in this context, will be to change the game so the good outcome becomes the rational one. Minimum game theory primer. By the way, let me feel imposter syndrome. How many people actually know game theory here? Okay. Thank you, folks. You can find me later. Okay, so in game theory, you have players who take decisions, and you have strategies that each player takes, are actions. You have payoffs, that what player gets as an outcome of their actions. In the SRE, it could be the velocity of the system, of the releases, could be reliability, pager load, risk, reputation, career, safety. And payoff is not necessarily money. It means something that person cares about. And then as an outcome, you have something that happens with the system. And you can have best response or not the best response. So the SRE way, SRE influence is not about persuasion. It's about the payoff design. We change incentives, we change the information that is available, but we make information available to those who are taking decisions, and we evaluate the risks. So the good outcome becomes the high reward outcome, so the Nash equilibrium changes for the better. And this is very well studied in the resilience engineering. And John Alspo, I don't know if he's here, he's working on this as well a lot. So we don't fix systems by telling people care more or try harder. This actually comes from this, from Edward Deming. And instead of this, we say, let's change how we reward things. Let's make shortcuts not as rewarding as doing the right thing. Let's change the way information is shared, make sure that everyone have access to the right information to take decisions. And let's make sure that the risk is shared. It's not buried by one person. And this way, there is no hidden toil and there's no hidden risk. The ownership have consequences and is understood. So let's see SRE work in this talk as a mechanism design for the game. And let's redesign the game so better behavior becomes the rational choice. So let the game begin. And remember, if you don't like a game you are playing in your life, you have control to redesign it. You just need to know some strategies. So let's start with prisoner's dilemma. In prisoner's dilemma, two people are trying to break into the house or place. But police catch them before they break into, so they are imprisoned for trespassing, which is the minor offense. Police suspect that they were planning actually to do something bigger. So police wants to discover and make them confess. So how do they do this? They use prisoner's dilemma. They put those two people in different rooms so they can't communicate, and they offer them a deal. They say that if you confess, you can walk away. But the other person goes for 3 years. If you stay silent, well, you will get 1 year. And the problem is there are two players in this equation. So if both of them stay silent, both of them will be in prison for 1 year. But if one of them confesses and another stays silent, the one who stayed silent will be facing even bigger charge, will be 3 years. If both of them confess, they will get moderate charge, which is the 2 years. So you see this trade-off. If they could speak to each other, they probably would have agreed that they should stay silent because the overall outcome would be more positive for both of them. But at the same time, those decisions are being made in isolation, and each one of them would be looking for the best outcome for themselves. So each one of them say, well, I want to confess because I want to walk away. And if both of them confess, they will both go into prison. So the overall outcome of the system will be less optimal than if they stayed silent. So two people can each act rationally and still end up with the worst outcome, so which is what prisoner's dilemma show. And if I optimize for myself and you do the same, we both lose, even though cooperation would be better. And in engineering, this is how silos or information that is not shared and the local wins quietly create this global pain. And the prisoner's dilemma is also a proof that everyone did the right thing, but something didn't go as expected. Now, this is AI generated, but everyone recognizes the landmark that was inspiring this picture. And in the prisoner's dilemma, cooperation benefits everyone, but defection is locally rational. In engineering terms, investing in reliability is helping the system, but I have my roadmap to meet. So I need to close all those feature requests before I invest in this big thing. And that's how prisoner's dilemma looks like. So the least desirable outcome is also the most stable equilibrium in this case. So it's short-term rationality that produces long-term instability. And there are ways to fix it. I won't just expose problems, don't worry. The fixes will come, because I'm a mathematician, remember? Let's analyze game of freezing deployments. So we have 3 players. We have dev, SRE, leadership. We have freeze or ship. And freeze becomes dominant usually in the system where rollback is very hard, telemetry is weak, and the post-change blame is very high. So, but freezes backfire. We all know from the experience because your big batch of change, you accumulate a lot of changes, you have big blast radius, and you have a lot of unknowns. And Dora studied this extensively and published a lot of work. So we had Nicole Forsgren here in this conference. If you're not familiar with Dora, I really recommend. So I built here this picture that shows the trade-off between throughput and stability. And Dora proves that teams who leverage both high speed, high throughput, and high stability are the most performant teams. But freeze at the same time sometimes is perceived as a best response. Why is that? So because freezes are Nash equilibrium, because they're stable, they're rational, and they are suboptimal. This is the same thing as the prisoner's dilemma. Shipping carries asymmetric risk, because when I ship, I will get paged. If something breaks, I will have incidents, I will need to explain them, I will need to wake up in the middle of the night. So it's logical choice to freeze. And it's not a people problem. It's really the system. It's a game designed this way. And freezes rarely start from scratch as a bad idea. So systems don't start with freezes. Systems start with, we ship fast, we do the right thing, but then incidents start happening. So there's a global harm caused. And it's start eroding the trust. Because every time release happen, the people around see there is an incident. On-call engineers are getting called. So what happens? They start changing they change and they implement the freeze. Decision-making becomes centralized because someone needs to decide if you do or not. And then the degree of freedom is reduced. So engineers lose the ability to influence when do they ship. And why does it happen? Because decision makers who decide on freezing the deployments, they don't have the same exposure to information as people who are actually close to the system. And safety become undistinguishable from fear. And this is actually a phenomenon that is called information asymmetry, where the players in the game have incomplete knowledge, but still need to take decisions. And this is a quote here from Friedrich Hayek. When information is unevenly distributed, decisions optimize locally but fail globally, which is, again, the prisoner dilemma all over again. In the game theory, there is this model called the principal-agent problem, where the principal is the party that sets the goals and the agent is the party that executes the work. And SRE often involves Bayesian game, where players act on private information and guess about other teams' decisions. And that's just how system is designed. So the product group might have looming deadline. Finance team may have some not fully understood risks, so they will defund something. So this leads to mutual miscalculations, and there are necessary freezes or budget cuts that do not benefit reliability. On the other hand, SRE work is never one and done. It's a cyclical work, it's repeated. So there's a game for this as well called a repeated game. And we will also review this one. What do we do about the information asymmetry? We can't keep it there. We need to make sure that all decision makers have exposure to the same information so they can take the best decisions. And the engineering systems are really decision heavy. We need to take decisions on all this architecture, capacity, incident response. And we need to understand the system end to end, but those who take decisions about freezes or other bigger changes or investments, for example, they also need to have exposure to this information. So people closest to the system see the risk and they see failure modes. But the people who make decisions, they see outcomes of those decisions of the agents. And they see constraints. So what do we see here? We see the incentive model is mismatched. The people who are deploying, they are incentivized for deploying faster. The people who are funding it are incentivized for bringing more stability. So how do we solve it? Well, we have a solution for this one. It's a structural or decision-making and technical approaches. For the structural, we can share ownership so pain isn't hidden. And in decisions, we ask who knows something others don't, and we move authority there. Because those who understand are the ones who will most likely decide the best outcome for the system. And technically, we surface uncertainty and failure modes early. And SRE won't improve the decisions. SRE just improve who knows what and when. And this way, decisions will naturally become better decisions. And when information is asymmetric, even good people can design bad systems. And it's not about the people, it's about the system that makes it possible. This is another quote. I really like quotes, and this allowed me to add this lovely AI-generated picture as well. When information is asymmetric, rational players still produce suboptimal system outcomes. Now let's try to model this freeze equilibrium using prisoner's dilemma. So here we have the high penalty environment where we will model how people involved in this game feel about freezing or shipping. And in this case, the freeze seems to win. Each number inside the cell represents a triple, which is the dev, SRE, and leadership. And the number means how happy or how comfortable the person is about that specific action. In this case, dev decides to freeze its 2, meaning that low velocity is bad, but they have high confidence that things won't go bad way. They have no risk for the blame, so their reaction to freeze is mildly positive. Then we have SRE. SRE is very happy in this case, because they said pager will stay quiet, the blast radius will not be big, toil will be predictable. This is the best outcome in this specific system. Leadership is also happy. Everything is predictable. There are fewer incidents, reputations feel safe. This is a short-term win for them. But what can we do? This feels safe, right? But when we look at the whole system, it's actually not the optimal outcome for the whole system. We need to change what is making those decisions logical. So how do we change this? Well, we make shipping cheap. We use canary, we use progressive delivery, we fast rollback and make everything reversible easily. So we have SLIs tied to user experience. Freezing needs to become expensive, so it becomes a second choice, not the first choice. Because by freezing, we need to surface how much risk will accumulate. So those who take decisions will understand that freezing is actually more risky than shipping. But shipping needs to be really predictable, easy, and reversible. And finally, we need to replace judgment with policy. We need to tie releases to specific guardrails and don't make it binary, just go or not go. They need to be an error budget or any mechanism that makes sense for your system that will allow you to make decisions based on data. So price risk, don't assign blame, and use error budgets. I will summarize that so I don't go into detail. Now we redesign mechanism. Let's assume that that organization, that fictitious organization we had, implemented all those. So it's safe now and it's easily reversible. So now the balance shifted. And I'm sorry if that picture is dark on dark, I'm just realizing now. I will just speak you through the numbers. Now ship is the winning choice. You have 5, 4, and 5. Dev says 5. We have high velocity, we can keep shipping features fast. We have high confidence because if something goes wrong, it can easily be reversed, or maybe there is a feature flag, we can just switch it off. And there's a low blame. There is no, all risks are understood. SRE also think it's a great idea because pager load is acceptable, things are predictable, blast radius is minimized and recovery becomes a routine, there is no heroics involved. Leadership also loves it because business moves fast, incidents are contained, and they like to have predictable outcomes. So now we shifted our game to the win-win by applying mechanisms that can make the right choice the better choice, the easiest choice. So let's look at another game called Stag Hunt. In the Stag Hunt, 2 hunters go to the forest and they have available hares or stag. And if they both hunt hares, they will bring home moderate reward. If they both hunt stag, they will bring home big reward. If only one of them will hunt stag, they will bring nothing because they need 2 people to hunt stag. So this also translates in the matrix. I learned that the game theory is all about those little matrices, which is awesome. So if both players hunt stag, the outcome of the system is 3-3, so it's a big reward. If they both hunt hare, the outcome of the system is moderate, but still both of them get home something. But if only one of them commits and another still rely on the safe hare hunting, then the one who committed will bring home nothing, and the other one still brings moderate reward. So Stag Hunt is a coordination game. Everyone wants a big win. Everyone wants that big reliability win that they really will make a difference. But everyone needs to commit to it. And in SRE terms, the stag is the real reliability work, like a big refactoring, a big mitigation, automation, or big platform fixes. But the hare is locally safe. It's like small patches, small freezes, incremental work that avoids risk. And the trap is this. Hunting hare is individually safe and more rewarding individually. But if everyone does it, the big reliability win will never happen. So why teams get stuck in this bad equilibrium? So the Stag Hunt describes coordination risk. If I invest and others don't, I will go home empty-handed. So it's a too much risk. And that's why you see chronic freezes, postponed migrations, reliability debt. And that's why system gets into this bad equilibrium where choosing the hare is the logical choice. Because people locally prefer stability. So teams don't avoid the Stag because they don't want reliability. They avoid it because they don't trust coordination. And if this is the problem, then that's the problem we need to fix. Now let's look at another game, Bayesian game, which is about decisions that are made based on incomplete information. An example of such game would be poker, where you know your cards, but you don't know your other player cards, and you need to make decisions based on that. In Bayesian games, players act without full visibility. Teams don't always know where system fragility lies, where failure modes are, what is the risk priority, and this uncertainty drives defensive behavior. And in good teams, this behavior may lead them to the wrong choices, because they will take cautious choices, and cautious choices will fail globally. And here's the quote, which is so fresh because it was spoken yesterday at AMA with John Alspo, that most missing context isn't hidden, it's assumed. People don't share what they believe, everyone already understands. And if I didn't remember word by word, I apologize to John, I can be corrected. Another game called public goods. Public goods are things everyone relies on, but no single team really owns fully. And the cost need to be shared as well. For example, batch run call, tooling, documentation, everyone benefits regardless of who paid the cost. And it's rational to free riding in a system where the benefits are shared, but the costs are local and there are no incentive to actually invest in that. So without explicit mechanisms of the incentive, public goods don't disappear. You just stay permanently underfunded. So reliability work is a typical example of public goods. Cleanup alerts, everyone benefits. But that one person who did the work, they will pay with the time, toil, and the pager fatigue while they're working on that. So the benefit is shared, but the cost is buried by one person. And it's rational to hope that someone else will do the work. That's what game theory model explains. So that's not a bad behavior, it's just a good game theory. And in a poorly designed game, this results in the hero on call. It results in the docs and runbooks getting rotten, and the reliability work is postponed to the next quarter. That's the public goods problem. And that's not the quote, just like if reliability is everyone's job, it's no one's incentive. So it fails not because people don't care, it's because caring isn't rewarded. And let's look at some examples of public goods that you can invest today, or tomorrow when you get back to your retrospectives, and make sure that everyone benefits from this, but it's actually a repeated exercise. Retrospectives is a public good investment because everyone benefits from learning. One individual will pay the cost, but if it's continuous, it will be shared cost. And if you don't have equilibrium around postmortem maturity, you will end up having shallow postmortems and low follow-truth. So how do you do this? Well, you can use SLOs as the public goods mechanism. In this case, you have shared SLOs that are aligned on incentives between different players, and sudden reliability stops can be work that is shared by everyone. So you standardize them, you have error budgets, and they are shared and understood by everyone. And I will have a bit more about the practices later. But right now we reviewed 4 games, and they built on different types of failure modes, and they have same outcome. So if you look at the prisoner's dilemma, It fails because of the self-interest that system is built around, that all system fails. In the Stag Hunt, the trust and coordination. In Bayesian, it's about information incompleteness. And in the public goods is the unclear ownership and the incentive. So in this case, there's a good intent, but there's a local rationality that the system is not built to produce the reliable system, and system will fail globally. So what do we do? Those games are already stable. If they're already there, they must be running, and something happens for them to establish themselves. So how we can disrupt this run? So game theory also have models for this, which is great. So there is this thing called Stackelberg leadership, where one player commits first and visibly, so other players see it. And the power here is not about authority, like I told you to do something. It's about commitment. So one person commits, or one team commits, and just does the thing. And this commitment will give them power because it gives them authority. They know what to do, they are iterated, they walk the walk, and if they made it easy and desirable, others will join as well. So that Stackelberg leadership, for example, works in chess. You commit and you do your move. Other players will need to do their move according to your move, because now they probably can't occupy that cell or they can't go somewhere because your move influenced the whole outcome of the whole system. And here's that last note. It's not about starting to coordinate. No, you first commit and you walk the walk, and the coordination will come later. In Stackelberg game, what kind of commitment or moves you can do as an SRE? So far we talked about failure modes, where a team can react to coordination problems, incentive problems, and uncertainty problems. And those are the ones you could try to address with the Stackelberg game. Stackelberg can flip that around. So when one player moves first and commits, everyone else rationally adapts. So if your first move is rational, the whole system moves one step forward for the rationality. And this way, by moving first, you influence what decisions are available to other players. There are more games that can help us to win this. But one of them, there are repeated games and evolutionary games. One of them is not good and another is good. So repeated games are good because teams remember past outcomes. They do something repeated. There's a lot of this in board games. You just do something every cycle. And reputation and consequence matter, and cooperation can emerge over time. And then there are evolutionary games, where successful behaviors get copied. And its may look good locally, but it actually may be very expensive later, because workarounds may outlive their context. Something that worked a year ago may not be relevant today, but teams just inherit that behavior and they just keep doing it. Things like, we will always call that person when something breaks. Well, that's a bad behavior, but everybody just falls on that because, well, we just know that the thing will be fixed. So norms persist even when conditions change, which is risky, which ties to that culture note that I made earlier. Let's look at an example. We had this incident and there wasn't a workaround. And it was successful, so teams will replicate the success, they will do it again because it worked. Then they will just consider, all team will consider this thing is the standard practice now. And they won't question it anymore because everyone will see it as a norm. And at that point, this game is no longer being played by people, it's being played by culture, because it's everyone assumed truth. So how repeated games and evolutionary games come together? So in repeated games, you have memory of past interactions and you're actually intentional and rational. So it's a short-term thing and you can adjust your choices. For example, air budgets will influence your next quarter, so you repeatedly are trying to optimize your system. In evolutionary games, it's different. It's just things that stick as a practice over time. And it suddenly start being seen as a norm. And it's a long-term and example of this, like that's how we deploy here, so we just keep doing this because it worked in the past. Incident response is another repeated game, which is good. At the same time, incident response have some aspects of the prisoner's dilemma and public goods together, because there is some shared knowledge and shared assets in it, and there is some lack of communication between people that may slow it down. And this is in the badly designed system, obviously. Once you are aware of those things, you can fix it, and then it won't be a case. So what is happening? Every incident teaches the system what good behavior looks like. Then payoff repeats. So strategies stick. And then things may get into the bad equilibrium. The heroes are raising. Automation stays next quarter because there's this hero that can fix it when things break. And then pager load concentrates on few unlucky people. So how do we change this game? Well, we reward prevention and not just recovery. Instead of just celebrating we fixed another outage, we look into what did we do so it never happens again. And we need to track it as well. We fund automation like a product work, and we rotate and share operational burden. What do we measure in incidents? I heard frequently in the discussion groups that it would be time to mitigate. We need to introduce additional measures like time to detect, toil of hours per incident, coordination cost, which comes, how many people are involved in each incident, how many handoffs are happening, how many escalations hope, so the incident finally finds its team. And as a result, things will change, things that you can probably measure. Things like incident handling effort over time will reduce. The automation and self-service coverage will improve. The cognitive load during incidents will improve as well. And the confidence to ship safely will also improve as a result. So there are some things that are hard to measure and tie to that specific action that you were implementing, but at the same time, you will see the change in the system over time. And I was asked a few times, like, how to make reliability work visible. And I had another 60 slides about this, so I needed to move them to appendix. And I may submit another talk about this, but I just added this one slide about how to make invisible work visible when nothing breaks. Because the success in SRE means that nothing breaks, right? Things are stable, we are releasing fast, and everything is predictable and visible. But then those who are funding those priorities, if nothing is breaks, they think like, well, then SRE is doing nothing probably. So we need to suggest different kind of indicator that show the state of the system. For example, coverage of user journeys with SLI, error budget burn rate and volatility, like calm error budget burns or spiky. Detection latency for SLO threats, time to signal. And you can frame impact as a risk retired instead of incident survived. And yes, I have another slides there, but next talk. How do we make retrospective stick? And I'm realizing I need to accelerate. You make learning visible in the system. You need to have actions linked to your retrospective and also have them linked to your SLOs. And you track the fixed completion rate. You don't just create that action and then you never look at it. You measure repeat incident rate as well. And you make learning collective because the quality of retrospectives decay if nobody looks at it. If you're just expecting the person to do the best job by documenting it and nobody ever looks at it, you can be sure that the quality of those write-ups will decay. So you need to make sure that you create a culture about reviewing them regularly with the team and rewarding the process of learning. And don't forget, if you just chase metrics, you will fall into the Goodhart law, that metric becomes your punishment instead of becoming your mechanism of improvement. And you are almost ready to design the game so the right outcome wins. You make risk legible. Risk threat modeling, we spoke about it a lot in the observability discussion group. Instead of measuring lagging indicators, like things already happened, let's analyze them and learn from them, which is very useful. Also do the proactive indicators. Model the risks of your system, even if you are using probabilistic measures. How frequently that thing may happen, even if it never happened before. How big will be blast radius of that thing? And then make it known, make the decision of prioritizing those fixes, make it owned and shared so everyone understands what may break in addition to what already broke, which comes from the retrospectives. So you make those decisions collectives, and as you remember, you move first because Stackelberg. So to design your game, it's just those 5 steps. You see who are your players, if it's a team level, if it's organization level, how big is the game you're designing? What are the strategies you have today and where they are failing? What kind of model from game theory it fits into? And what kind of model could fix it? You identify what are the payoffs that are making people choose what they're choosing. And you see what equilibrium your system is now and where do you want to be. And then you start changing rules. And that's where I have very dense slide next, not this one. So just to summarize, teams make interdependent decisions where whatever I decide will influence other people's decisions. And me being rational individually doesn't mean that the whole system will benefit, because I may not have the whole information available to me. So we reviewed few games, and I have this slide if anyone wants to take picture. I summarized for you different failure modes of each of the game theory that introduces failures into the system. So the Stag Hunt is about trust. The prisoner's dilemma is about incentive alignment. Bayesian game is about uncertainty and incomplete information. And the public goods is about free riding. And each one of them have a different mechanism to be improved. So once you understand where your failure modes are, you can obviously make it better. And depending on the size and maturity of the team or the system, you may want to focus on specific game theory methodologies first. For example, for the smaller team or the early software, the public goods probably is not a problem yet. And information may be able to fit in one person's head. So Bayesian game also may not apply. So for the smaller systems and early teams, you may want to focus on the Stag Hunt, on building trust, and on a prisoner's dilemma, on aligning incentives between decision makers. And once your system keeps growing, you start accumulating public goods problem. So make sure you don't miss that moment where you need to intervene and start designing incentives so the ownership of public goods is actually understood and funded. And make sure that you have good information flows so the Bayesian game do not impact you negatively. And finally, make sure that you continuously understand if you are evolutionary, didn't stick specific practices that don't make sense to be in your system, because they become your culture and you may not want them to prevail. But once you're intentional and you understand what is happening, then you will be able to make it better. So SRE intervention comes from start first, start doing the thing, learn from it, start designing mechanisms on how to do it better, and then keep repeating, and others will come along because this will become the best choice. And that's the last slide. Your system isn't broken. Your system is doing exactly what it was designed to do, but you can redesign it. Thank you.